So when we say that all matter is made up of the atoms of approximately 100 elements, what we really mean is that everything in the universe is made up of those first 100 or so atoms. The first 92 atoms on the periodic table are the only naturally occurring atoms. There are many more than that on your periodic table, and as you get into those higher numbers, we start to see some synthesized atoms, those that were made in a laboratory setting. This is review for some of you, and if you want to advance to the next portion of the notes, that's fine. So the atoms are made up of protons, neutrons, and electrons, and you can see here that we've got an electron cloud, which is where our electrons have a high probability of being located, and then the nucleus at the center is made up of protons and neutrons. And a key note here is that atoms will combine in predictable numbers, and we're going to see that in just a minute. So elements are substances that are made up of only one type of atom. A sample of copper is only going to have copper. If it's a pure sample of copper, it's only going to have copper atoms in it. A sample of bismuth, which you had in your first lab, is only going to be made up of bismuth atoms. And the atom of copper is different than the atom of bismuth. They each have their own unique properties that makes them distinguishable. And so the element is the simplest form of matter that has those unique set of properties. Once we get smaller than one atom of something, then we're into a whole other realm. And so matter, the formula unit for matter, is the atom, and that's the smallest or simplest form of that. These are two different examples of elements. We have on the left a greenish yellow noxious chlorine gas, and on the right you have a very soft sodium metal that is housed in some mineral oil to prevent it from reacting. Sodium is very reactive with water, even water vapor from the atmosphere, and so in order to prevent it from reacting, you have to store it this way. I'd like you to make note of how the element symbols are written here. The sodium has a capital N and a lowercase a. The chlorine is a capital C with a lowercase l, that is not an I, and then there's a 2 subscript on the chlorine. The subscript basically tells us that 1 unit of chlorine gas is actually 2 chlorine atoms bonded together to form a chlorine molecule. Chlorine is a reactive gas that you will not find by itself. You cannot find just a chlorine atom by itself. So when you have a pure sample of chlorine, it's going to be a sample of chlorine atoms bonded together. That's known as a diatomic molecule or a diatomic element. It is still the element chlorine, only there are 2 atoms bonded together to form the smallest unit. The sodium, you'll see, is just 1 sodium there. Sodium has metallic bonds, and we'll explore those also later on in the class. It's important that you get the notation correct when you write the elements and the formulas for either compounds or the chemical symbol for the element. You always use an uppercase letter for the first letter, and if there is a second letter, that letter will always be a lowercase letter. So if you're in the habit of writing uppercase letters all the time, make sure that you distinguish that when you're writing the element symbols. So you can see that the sodium and the chlorine each have very distinctive properties. The chlorine gas would definitely not be a good thing to inhale. Chlorine gas was used during World War I, I believe. Sodium, if you put sodium in your mouth, which most of you guys always like to ask what would happen if I ate this or licked this. If you put the sodium in your mouth, then it would definitely react and you would probably burn your mouth. You'd have a little explosion going on in there. So compounds are substances whose particles consist of more than one type of atom. A compound is a substance that contains 2 or more elements chemically combined, which means they are bonded together in a fixed proportion or ratio. So this is really important. Here we have that sodium and the chlorine that we saw in the previous slide as elements are now bonded together to form a unit of salt. And these pictures, you can see that there's some salt crystals that are showing. They have that classic cubic structure. So if sodium were to react with chlorine, you would form salt. And you can see that 1 unit of the salt is a combination of 1 sodium atom bonded to 1 chlorine atom. We no longer see Cl with a subscript 2 after it. So the salt or sodium chloride formula unit is a ratio of 1 sodium to 1 chlorine bonded together. And when it is bonded, we call this sodium chloride. And you can see that the properties of the sodium chloride are completely different than the properties of the chlorine gas and the sodium metal. The sodium chloride you put in your mouth, unlike sodium metal or chlorine gas. You don't want to inhale chlorine gas. Both of those could do you great harm or kill you. Salts will only kill you in the long run if you eat way too much of it over the course of a lifetime and you end up with high blood pressure. So very different properties, and the key idea here is that when you take these elements that have their own unique properties and you bond them together, they combine, the properties of that compound that formed are completely different than the properties of the elements that made up that compound. So a couple of key notes here. Compounds can be broken down into simpler substances by chemical means, but elements cannot. So remember that with an element, the atom is the smallest unit of matter, and that cannot be broken down any further and still retain the properties of that element. Compounds can be broken down, that sodium and chlorine can be separated, but it takes a chemical reaction to separate those. Compounds have different properties from the elements that made them. We just discussed that on the last slide. The chlorine gas and the sodium metal have different properties than the sodium chloride formula unit has. Also note that chemical changes are not easily reversed. Some chemical changes can be reversed, but there's energy inputs there that are required, and it's not always an easy thing to reverse that. If you burn a piece of paper, you cannot get that piece of paper back into its original form. So some chemical changes are not reversible. Some are, but it just takes energy to do it. So here we have just a list of some physical properties of matter. Every sample of a given substance has identical intensive properties, and intensive properties are properties that go along with the element. Doesn't matter how much of that element or that substance that you have, the intensive properties will always remain the same. So if I have a thin copper wire or I have a big glob of copper, the properties of those two different pieces of copper are going to be the same. Some of those properties are melting point, boiling point, density, viscosity. Viscosity, for those of you that don't know, is a measure of a fluid's resistance to movement or resistance to flow. So a substance that pours very easily, like water, would have a low viscosity because it has a low resistance to movement. Something like molasses or syrup, a thick syrup that doesn't flow very easily, has a high viscosity because it has a high resistance to flow. That's a physical property. The state of a substance, whether it's in solid, liquid, or gas form, is also a physical property. The solubility of a substance, can it be dissolved in water or alcohol, is another physical property. Color is a physical property. Conductivity, which some of these things you tested when you did your observations in that first lab. So conductivity is the ability of a substance to conduct an electric current or to conduct heat. Miscibility has to do with how well a substance can mix with water. And magnetism, of course, you all know what magnetism is. So this last note here, an intensive property depends on the type of matter in the sample and not the amount. So whether it's that thin wire of copper or a big chunk of copper, they're going to have these same properties regardless of how much it is or what form it's in. So this ends the notes for this first section, and in the next portion we'll talk more about chemical properties and distinguishing between physical changes and chemical changes in a reaction.